Okay, so I'm going to take us into some source effect stuff now. I'll preface this by saying a lot of this is sort of the framework for what's going to be a parameter study, and I'm hoping for some input on what you all would like to see me look at with dynamic modeling. So just a brief outline. I'm going to talk about just some issues in the dynamics of fault branch systems, some advantages and disadvantages of using dynamic rupture modeling as opposed to the various other techniques we've discussed at this meeting. I'm going to talk a little bit about the branch fault benchmark that was done for the rupture code validation workshop, because that's going to be the framework for how I'm setting up my models. And then lastly, I'll go back over what I am planning on doing. And you see the phrase preliminary results up here. I apologize in advance for the fact that those do not yet exist. I'm still very much in the setup phase, but that's exactly where I need your input most. So, some of the general questions that come up with modeling rupture on a branch or a splay, and this is again on all strike slip. I'm going to try to avoid the phrase complex because this is not that. But if someone please catch me if I do say that by mistake. So the questions are with this splay are can rupture propagate through all three limbs of such a system, that is the branch itself and the primary fault on either side of the branch point. Whether or not that is possible, what are preferred rupture patterns and which parameters control them. Then if that splay does rupture, is the rupture behavior continuous from the main fault? As if, do the rupture contours continue going as if there were no discontinuity, or do you actually have to have a renucleated rupture on that splay fault? And then the stuff that gets more at what this workshop is how does the ground motion from rupture on such a system compare to that to rupture on a planar fault, both in terms of pattern of ground motion and in terms of intensity? And then how does the motion between the main fault and the splay compare to the motion on the outside? And that particular question is especially applicable to the Diablo Canyon case. So I'm also, in this talk, mostly going to be, that's the wrong side, mostly focusing on the ones that are about the dynamics, because at this point, I don't have any ground motions yet. So I'm going to be showing a lot of pictures similar to this. So one of the main problems in a splay fault geometry is, well, there's a lot of them. One of them is whether it's a releasing branch or restraining branch. And I mentioned this earlier. Basically, depending on the direction of slip and the geometry of the fault, the branch point is either clamped or unclamped, depending on the slip direction. So in this case, we have a releasing branch. And so basically, as rupture approaches this point, if everything is sliding right laterally, this chunk is pulling away from here. And so this is dynamically unclamped. You're relieving some normal stress. It should be, in theory, easier for rupture in a purely dynamic sense to take off in there because you're relieving some normal stress. And conversely, if you put the splay on the other side of the main fault, you're slamming this side of the fault into the branch point. You're clamping it tighter together, increasing the normal stress, and it's harder, in theory, for rupture to go through there. And some of the step-over models I've done, it actually turns out that there are some cases where you're dynamically clamping and it's still favorable. I'll get to that in a minute. It's much more complicated than just releasing is easier and restraining is not for through-going rupture, but that's the most basic effect here. And so some questions within that is the clamping effect the same if rupture comes from the interior or the exterior of the branch? So previous modeling studies, including the benchmark, have the nucleation, forced nucleation outside the branch, just going towards it this way. I'm curious about what happens if you go this way, because this block in here is kind of rotating based on, well, you're compressing this way, or if this is rupturing, then you're kind of pulling it out. So the dynamics get much more, the kinematics get much more complicated, depending on which way you're coming from. And certainly if you're coming from the branch, it just changes what we think of as restraining or releasing, even though you would still call this overall a releasing branch. And so both what is the effect of that clamping or unclamping, and how does it change depending on where you're coming from. And I will note in a constant traction model, when you're not, if you are existing in something that's not a regional stress field, then flipping the branch would be equivalent to reversing the slip direction, but that's not necessarily true a little later on. Another question, as I was already getting at, is the nucleation point. How does that affect what's going to happen with a rupture on this system? Again, the benchmarks and existing studies tend to start kind of outside here and go towards the branch. And indeed, things like the USURF workshops tend to sort of work way against backward branching, like way against something going this way and then that way. Just what might happen? That's one of the questions. The choice of nucleation point affects the possible geometries. It affects the dynamic stress changes. It affects the directivity as well. So both in terms of which direction it's going in and also how close you start to the branch will have some effect. So I've put my proposed nucleation points all at the ends of each section to basically maximize the effect of directivity, because the longer you have a rupture front going, the more energetic it becomes and the more likely it is to set off rupture on some splay or some step over. So if I were to start a rupture here, I would probably not be able to get propagation as far onto either one of these faults as starting down here. So other points that I might test in the future would be in the middles of these segments or closer in to the branch point. But as a starting point for what I want to do in this parameter study, I want to investigate the ends of each section and also at the branch point itself. And in this case, the nucleation would be on the main fault and not at the tip of the branch fault. And sort of my reasoning with that is, well, aside from just wondering what would happen, which limb would be preferential when you're starting between all of them, is if you were to have a rupture that was on just the splay and it ended and didn't transfer onto the main fault, this would be a spot that has a nice concentration of shear stress. We'd have a nice increase in Coulomb stress right there, so it would be a probable location for or certainly a favorable location for a future rupture. So those are things I want to look at. Branch angle is a big one. Here's some figures from previous work. I mean, as we've talked about a lot, and as the angle influences whether or not rupture is going to propagate and what the rupture pattern is going to be. So this figure on the left is from Kame et al. 2003, which was a study on branch faulting and how initial rupture velocity and branch angle and regional stress field angle all affected the ability of rupture to propagate through a splay fault system. This is just one example. So all four of these have the same initial rupture velocity, the same stress field orientation, and what's varying in them is the branch angle, and they also all have the same nucleation point. And so as the branch angle changes, in this one, the red indicates the part of the fault that did rupture. So for these guys, there is no rupture on the branch, but as you put it on the other side, I believe this is the restraining side and this is the releasing side. You start to have rupture on the branch, but for a shallower angle, or a smaller angle, you go through the whole branch, and as it gets wider, you get more of the main fault and less of the branch fault. And so questions like that, this is just an angle effect here. The whole paper has a whole bunch of other cases, and whether they're varying the rupture velocity or the regional stress field, you still see very different looking behaviors just depending on the angle. And the figure on the right is from a paper I did on stepovers, on double bends. So I guess I should have put the geometry up there, but it's something that, two parallel segments joined by a linking fault at some angle, all strike slip. And in that case, I found that the angle very much controlled whether or not rupture was able to go all the way through that zigzag or whether it stopped somewhere on that middle segment. And so if you consider that middle segment, it's not completely analogous because there's no straight fault. The rupture could keep going on rather than taking the bend, but still definitely the angle, this side to the left is extensional is releasing, and to the right is restraining. And so and rupture kind of stopped propagating through at where this green, which, well, all of my labels actually completely disappeared from that. The green is S, it's fault strength. Those were all labeled, and they are now gone. The important one, so this is normal stress, shear stress, strength excess. The important one, though, is S as a fault strength parameter, and you get this goes to infinity fault strength, and that sort of marks the end of where rupture is able to propagate through. So I anticipate seeing some sort of similar effect with the splays, but with the added complication of, does rupture take the splay or does it ignore it? So angle is very important, and it's also one of the easiest things to vary in a parameter study. Aside from angle, it's one thing to have the angle of the display, but the angle of the regional stress field makes a big difference as well. So these annotations they also come from the Kame et al. Paper. So with phi being the branch angle and psi being the angle between the main fault and the regional stress field. And so these dashed orange lines are supposed to be just some arbitrary regional stress field orientation, and so it hits the main fault at a different orientation than it hits the splay fault, and so as such, even a completely uniform regional stress field is going to resolve differently on a fault segment of different orientation. And so you get the problem of not only what is dynamically favorable or unfavorable based on the clamping, but what is statically favorable within that stress field. So something that might be dynamically clamped together with really a lot of additional normal stress just from the direction of slip might ultimately in the regional stress field still be an extremely favorably oriented fault section. So you have this interplay between the dynamics and the regional stresses. And so in this case, actually switching the side of the branch but keeping the same direction of slip is not equivalent to switching the slip direction, even if they were both right lateral here, and you're hitting this differently. And so in this case, I would run a right branch and a left branch in both right lateral and left lateral, and then at a whole suite of different regional stress orientations to see how that affects things. And so with each slide, I'm drastically increasing my parameter space, and there's a million things I could vary, and that's one thing I want to know from you is which ones you would like me to get at first, but I'll get to that. So these are all a lot of dynamic concerns with these. Of course, all of them will control, again, things like, does rupture just take this bend, or does it have to stop and restart? And I imagine that effect, that effect is something I'll track as well with these, looking at the slip rates. And the last one is the effective velocity structure. It's not just a ground motion effect. These, I will mention right now, these are qualitative descriptions of ground motion. Don't take these values at face value. These are from some simulations I did of the San Jacinto fault in Southern California, and they're just dynamic models. They are only up to 1 hertz, and they're to illustrate just sort of where the stronger shaking is and how including a velocity structure or not affects it. I know Tom doesn't like this fault geometry. He's looking at it. But basically the take-home point here is this one is in a homogeneous half space. The rupture pattern, the ground motion pattern is still quite heterogeneous, just influenced by the geometry. But as soon as you put in the velocity structure, the SCAC CVMS, the pattern of ground motion changes. There's a larger area of strong motion here. You get San Gorgonio Pass, the waveguide that's pointed out in every shakeout, everything lights up. And that's just, but also importantly, it's not just a change in the ground motion. In the case of a half space, the rupture is able to jump this step over and renucleate and keep going down the fault. And including the velocity structure, the rupture is no longer able to jump. So in addition to affecting the shaking that you're getting out of this, it could actually affect the shape of the source. And so that's why it's important to include that in the dynamic models, even if you're not necessarily getting your ground motions directly out of dynamic models. So I want to test several different velocity structures when I do this parameter study. I want to do just the homogeneous one. But then a Northern California example, a Central Coast example, specifically looking at sort of the Yellow Canyon area again. And then a Southern California example, just to look at how these different velocity structures might affect the splay faulting behavior in these different areas. And another question I have for you definitely is the question of a 1D model versus 3D. I know a lot of you use 1D in what you're doing now, and it's certainly simpler to implement. This model, these are 3D, and I can implement 3D if I have it, but it's a question of what's in line with what you're doing. About to ask something? Or? Okay. So that's another question for you. So those are all the things well, at least many of the things I'd like to consider in what is turning into a very sweeping parameter study. So the questions of what does dynamic modeling bring to this table? There's some advantages and disadvantages. A major advantage, of course, is that you have the full physics of the rupture. You have all the equations of motion and of elasticity and of wave propagation. You don't assume any magnitude or slip distribution. You just tell it some stresses and a nucleation point, fault geometry, material setting, and it calculates the slip rate and the total slip and the rupture extent. It does all of that. And so you're not predetermining anything. There's no issue of having to make the faults a certain size or a certain depth to fit something. That all comes out of the physics of the model. And also, it can really give a picture of the source evolution rather than just a snapshot like I showed you on the previous slide. You can really watch the source evolve, and actually it allows you to better sort of, when you look at the ground motion plot and go, okay, so there's this thing that happened here at this time, and then you can really trace it much more directly back to the source effect there, because you can look at both of them as an evolution of what's going on in the model. And it certainly allows very complex initial conditions. I can have complex initial stresses, velocity structure, fault geometry, all kinds of things. And so I can either make it as realistic as possible using things from the literature, or I can pick a parameter and then just go through it very systematically and really isolate the effect of that parameter. So it's powerful for either combining many effects or looking at one. But some major disadvantages, though, is that this is an extremely computationally intensive thing. It takes me, well, those San Jacinto models that were on the previous page, those took a day and a half each, and those aren't even very high resolution. So that is a disadvantage. Some codes are faster than the one that I'm using. Some are parallelized. The one I'm using is not. But even then, it's certainly slower than a kinematic model. And also, in general, the maximum achievable frequency content is lower than what you're getting out of a kinematic model or from the GMPEs. So for the preliminary branch fault stuff that I did run, that the rupture didn't quite finish. I didn't make the model long enough, but I can get up to 2.9 hertz, which is not really what you need yet. There are, again, other codes that can get up higher, but still, when you're talking into the high frequency stuff, the 10 hertz and things, you're not getting that out of dynamic models yet. I mean, a good thing is that this is limited primarily by the computational constraints rather than by the code, so it's not like there's some methodical or some conceptual issue with dynamic models being able to produce high frequency ground motions. It's just purely computing power thing. So basically what I would be using models for at this stage is mostly to generate sources, to get some sense of what these sources might look like, what the renucleations and or propagation might look like, what some patterns are, perhaps some probabilities of whether or not rupture will take the splay, and then that can be the kind of thing that can be used rather than some of the other rupture generators to take out to high frequency until several years down the line, 5-10 years down the line, when we can go higher frequency, when we have the power to do that, the computer power to do that. So in terms of the state of the modeling so far, there have been some studies. I cited the Kame et al. Study a couple times. And the branch fault benchmark has been a big thing in the dynamic rupture code validation workshop. So this is a slide from Michael Burrell, who is one of the main guys working on the benchmark. This is the SCEC benchmark, or not SCEC, the rupture validation workshop benchmark geometry. So they had a splay fault that had 16 kilometers of main fault, and then the junction point, 12 kilometers of splay, and 12 kilometers continuing main fault, 30-degree angle. And they tested this as a releasing branch and a restraining branch. And there was some discussion of how to actually parameterize the branch itself. There's a lot of disagreement on the earlier years of the code validation workshop was how do we parameterize this. And what they decided to do, there's another one of Michael's slides, is to treat the junction point, treat this all as having split nodes in there. And so that is how the branch is parameterized here. There are certainly other ways to do it, but that was what they decided on. And in the case of, I guess, many of the mesh generators, the way it does that is it has a sort of baseline size of element, and it gets, squished and morphed to create this branch shape. But this is what they're using, and so far it seems. Here's now a slide from Ruth Harris showing some of the results of the branch fault benchmarks. These are some axes got completely illegible. These are slip contours. Is the distant down dip and the long strike, main fault, branch, and a whole suite of different models. So everybody's agreeing pretty well on the main fault and the releasing branch. In this case, the rupture sort of renucleates a little bit, but it starts to disagree a little in the releasing branch. And in the restraining branch, there's a little bit more disagreement, but also it tends to die. The rupture tends to stop. So there's certainly an agreement in the extent of rupture in this particular single parameterization of the branch, even if the contours don't line up. But they're still working on these. I know this is an ongoing part of that workshop. And there's some ground motion results, and they for some off-fault stations. So this one is actually in the wedge right between the faults, so it's similar to the kind of location you might be looking at for, again, a Diablo Canyon sort of case. For the releasing branch, it's the overall shape between the different codes agrees pretty well. For the restraining branch, it agrees a lot better. And so they're doing pretty well. They're pretty competent that the codes are agreeing, and this is doing what they want. So there is this framework now for adapting the benchmark into the parameter study that I want to do. So in terms of what now I have done so far is a whole lot of setup. Another disadvantage, I guess, of dynamic rupture modeling is the setup phase takes a very long time to find a set of conditions that permit rupture at all. So I'm still playing with stress fields. So here's what I have so far. I'm adapting my geometry from the benchmark. So what I'm using is the main fault is 50 kilometers long. The splay comes off exactly halfway along the main fault. Is also 25 kilometers long, and I'm varying that angle. And I'm using the code fault mod. It's a three-dimensional finite element code, and this is my mesh. And so what I was talking about is the light blue here is the actual fault. There's some smaller elements around the fault to get higher resolution there, and then bigger elements a little further away. And so the mesh is actually morphed with the branch, so it starts as a nice square thing, and it bends like that. So that's what it is supposed to look like. It's not some strange error. When I first saw it, I was like, is it supposed to do that? But it is. So this is what I have so far. I have a mesh, which actually mesh generation is kind of a pain. So it's not a complete lack of data. So again, what I would like to look at in the course of the study and re-emphasize what I would like your input on what is the most important stuff to investigate, and if there are any particular cases that I should be looking at. I want to look at a right versus left branch, that is a restraining versus a releasing branch, with a right or left lateral slip. I want to look at 4 different nucleation points in the end of each limb and also at the branch point itself. Those 4 velocity structures, it's homogeneous, Bay Area, Central Coast, and Southern California. I want to vary the branch angle, and I want to vary the regional stress field. And it's a lot of things. So I believe this is my last slide, unless no, that's my last slide. So what I would like your input on, again, what are some concerns, what are some questions, what would be your priorities as someone who would be using these dynamic models as, I guess, as sources to then take out to higher frequencies? Kim?
Do we have questions from the DA team? Okay.
Hi, this is Jennifer. Question for you. You had mentioned that it's going to... Okay. You had mentioned that it takes about a day and a half to do the example that you gave that looked a little bit more intricate. For some of the simple geometries that you just showed, approximately what is the runtime? So if you are going to be, re-looking at all of the branch angles, the stress field, and varying all that as a sensitivity, how long do each one of those models take once it's set up? Is it still about a day and a half for each run?
It's a little less. So for the splay fault ones that I've done that turned out to have some wacky stress field that didn't work, it took about 18 hours to run the model and then a little bit longer to post-process it. But that's, eventually, I foresee this parameter study as being something larger than just this workshop, but I want to start with cases that are useful. So again, the code I'm using is not parallelized, which does slow it down, but I can run several of them at once because there's still multiple nodes on the cluster, so I usually have 3 or 4 running at once. But yeah, they take probably, when all is said and done, between running and post-processing, about a day each still.
A question that I had was, it looks like you'll be able to get a handle on the probability that you jump a branch or a splay as a function of nucleation distance, but I would imagine that's a highly nonlinear function. So how finely do you anticipate you're going to need to test nucleation points? I mean, right now it's very coarse. It's the end and it's right at the juncture. But how close on either side will you need to get to really be able to address that particular question?
So that's actually not something I can completely say until I start looking at it. I did a very similar study with stepovers and with double bends, and I started doing it, 10 kilometers apart, then I went down to 5, and right around right around the transition of behaviors, I sort of did every kilometer, and so I guess we'll sort of see how fine I need to get it to that on the behavior. But it is nonlinear. It has a lot to do with how much of the so when you get that Coulomb stress change pattern, it's of course not a block shape. It's a lobe, and so you'll get that renucleation if the amount of the lobe that crosses the next part of the fault is larger than the critical patch size for renucleation. So and it is very nonlinear.
Okay, and you mentioned the frequency, the maximum frequency range, and clearly that's going to have an effect on any ground motions that would come out of the model. But is there also there must be a sensitivity? I'm guessing there must be a sensitivity in how easily you can jump. I mean, is there a sensitivity with respect to the frequency?
The high frequency
resolution of the simulation?
I haven't thought about that. I mean, all of the rupture jumping simulations, the dynamic modeling studies of
They're done at what's possible.
Yeah, they don't go to high frequencies. Right. So maybe I don't know. It's something I guess I'm not equipped to look at yet with the computer power that I have. But that's why I'm stressing the point of using these as probabilities and as a rupture generator at this point, not as the ground motion calculation in and of itself.
Okay, so this is my last one. Okay. So you mentioned 4 different velocity models, and these are simply one-dimensional models at this point.
Well, that's something I wanted your input on.
Yeah. So what I'd be curious about is having velocity structure across the fault. So
like having a contrast.
A contrast.
And one thing I would like to do is pick some locations, not just go here's some. If I do go for a full 3D one, I'm not going to be able to just make up.
But maybe something rather more of a canonical type of.
Mm-hmm. I mean, I would be interested. A thought I had, and again, input would be to actually pick some location that is a real fault area, like say for the Southern California example, maybe pick the San Bernardino Valley and have the main fault be the San Andreas and the Splay be the San Jacinto, and have that contrast in there, and not necessarily have that then not necessarily say, hey, I'm modeling Cajon Pass,
Right.
but pick some places that do have a real contrast while also using values that are out there.
I don't know how the rest of the team feels about that, but personally I'd be interested to see what sort of impact that has.
I mean, my inclination is to use the 3D. That's what was in the other San Jacinto model I showed, and the basin just lit up. So.
But in that model, is there a velocity contrast right at the fault, at the size at the rupture depth? That's what I'm getting at. Is if you
not at the full depth of rupture, the basin isn't quite that deep, but there's definitely a contrast in here on the basin, so the fault goes through it. And there's actually even more of a contrast than is what is represented here. I had to clip this to get even 1 hertz.
I don't recall if you mentioned it, but are you proposing changing the dip of the splay? Because I think one of the things we learned from Ruth Harris last time is with different stress orientations, the dip angle influences whether or not this rupture is going to propagate onto the splay.
That's not part of what I'm proposing right now, and that's something that we talked about maybe doing further down the line. I think for now, it would definitely be similar to changing the strike angle. You're resolving the stresses on it differently, and so it behaves differently. But correct me if I'm wrong, Norm. You wanted this to be pretty much vertical at this point.
Yeah, there's what Katie's getting at is some of our splays might be a dipping, a vertical fault going onto a dipping fault, but the main concern I have is this becomes really interesting stuff, and all of us say, I'd like to see this, I'd like to see that. Julian is doing a broader science study, but for our purposes, what can we actually use to help us answer specific issues? So if it's velocity contrast across the fault, it's got to be, are we saying we would adjust our ground motion models? And if I don't know what's my reference point in the GMPEs, how am I going to implement that sort of a thing? So I'd really like us to get a list of topics for Julian that are focused on things that we're actually able to implement in some way or use to help inform parts of the models. And then there's a broader whole science problem that he's taking on that I think can deal with some of these other interesting but maybe not directly applicable topics for us.
I brought up the velocity contrast across the fault because I think that may have a very important effect on whether or not you jump on branches and the degree to which you do, when you do. And so for that specific question about what the probability is of trying to get at that, whether you want to splay and how far down the splay, I think having the velocity contrast across the fault would be important. But you're right, it doesn't. If our main motivation is to actually get the ground motions out, then having several one-dimensional models would help look at that effect. But I see there's a ground motion question, and then there's the fundamental question about what's happening at these junctures, and then maybe what do we learn from these, and how do we use that to inform the kinematic models.
But I would think some of the ground motion question is not just how hard is the maximum it could shake there, but what is the likelihood of that? So there is a definite velocity structure going on here. You've got some contrast, mountains versus basin, and the rupture dies, and so I don't know. I could see still the utility in both cases of contrast.
Yeah.
With a resource hat.
Sure.
This is can you hear me? This is Steve Day with a resource hat on here. I just wanted to mention that this type of multi-fault problem has been done with lateral velocity contrasts, and Sebastian Langer and others have done it. And
You did.
Doug is correct.
I did one too.
And I'm sorry, I didn't know about yours, but
It just came out a few months ago.
it's pretty convincing that it can be a big effect.
Yeah, I mean, the work that I did on it was, it wasn't 1D, but it was, like very blocky velocity structure, just like block, damage zone, block, solid rock around it. It definitely made a big difference in the width of the step over that could be jumped. So.
Ruth would like to add something. She's connected on.
Okay.
So Ruth, whenever you want, you can talk.
Talk. Ruth, you can talk.
Okay, thanks. So I agree with both Doug and Katie. The material contrast that, of course, Steve Day and I published on in '97 for 2D and in 2005 for 3D seems like it could make a really big difference. And Katie brought up the point that the fault dipped. So the Izmit earthquake, 1999 Izmit earthquake in the North Anatolian fault is a case where it wasn't a splay, but a branch, and it was an unfavorable branch. That was the last fault segment to go. And I did a study that Steve's also co-author on, in addition to Jim Dolan and Ross Hartlib. And I hypothesized that perhaps that last fault went only because of the dip of the fault. So if the last fault had been vertical, it shouldn't have gone at all. But I hypothesized that perhaps because the last fault actually had a dip to it, that's what allowed the earthquake to keep going even farther. It went another 20 or 30 kilometers beyond what might be expected. So perhaps also for the Splay fault case, it could make a difference. So that gives you a different size earthquake, different rupture extent, and I imagine that would also affect the ground motion.
Can you go to your list? So thanks, Ruth. So part of this is, from what I'm hearing right now is, instead of just different velocity structures, 1D, you want to have something with some contrast across the fault. So, and variable dip angles. So those aren't even on your list yet, right?
Well,
Or
the velocity structure was vague.
a
on
generic
purpose.
structure. Okay.
Because I wanted to know what you thought. But no, I hadn't put
But
dip
can
on
we-
there yet. But it's definitely, I can't edit the PDF
That's fine,
right
but
now.
can that be accommodated by two 1D velocity structures across the fault, or is it really alternative 3D structures? Does it have to be a 3D structure, or is it two U, or sure?
I mean, in terms of how I implement a velocity structure in one of these models, I just need to know what the values are everywhere in the mesh, so it doesn't, I mean, implementing it would be the same.
I'm trying to get some input or feedback from those. So those of you who have done this before, is it using a full
Use
I
closer to your mouth?
I think a generic model, just 1D models in contact would be fine in my view, but Julian's looked at this more recently and may have different view.
I mean, I would, either way, really. Again, it's what is, I mean, I'm personally interested in both the realistic complexity and also just the simple case. So it's, what do you need? What do you want to see first? Would it be better for me to actually, take a real one out of the CVM, or just pick some values that are representative of, say, Central Coast rocks or Inland Empire rocks or whatever?
We want to capture a case that we can apply, right? as one of the suites that you're doing. But I think we need to have on here then a contrast across the fault and maybe a couple of different contrasts,
Yeah.
and variable dip angles on the Splay fault.
On display.
Okay. Are there any other comments?
Kim's hands was up a second ago.
Let's get
Yeah.
some more comments from the back.
This is Kim Olsen. Just a comment to both what Doug mentioned, the frequency content, and Julian's comment on computer power. it's actually possible to run dynamic models up to 10 hertz, and it's being done in Steve Day's group right now with using the rough fault methodology. So
I don't know why I thought you were only going up to 5. Sorry.
this is and that's using complexity through the roughness, fractal roughness of the fault. So one question is, as you go to higher frequencies, you will have to consider how to get that complexity in, either using the same kind of roughness on the fault or stochastic stress field or something else. Otherwise, you're not going to be able to capture those higher frequencies.
And I can already implement stochastic stress fields. That's a thing I didn't even bring up here at this point because I was treating it again more as a source, like a probability and an overall shape of rupture. But I can absolutely, on top of any stress field that we include here, add stochastic stresses, different realizations, like we've been doing with the San Jacinto.
So the computer power is certainly there. It's we're running parallel codes routinely on tens of thousands of processors. So
I need a parallel code.
It might be a limitation for you right now. So maybe you should bug Michael to get your code parallelized, because you can do a lot more with a more efficient code.
Yeah, I would definitely, that is a limitation. If I could fund Michael to do it, I would.
He's been talking about doing that for years.
Yeah, he's definitely been talking about it, but I from what I understand, it's a funding thing. But Ruth would know better than I would.
But there are codes out there that are parallel and can do stuff like this.
Yeah. Okay. So you're,
Ruth, did you want to add something?
Yeah, I just, in terms of our code comparison group where we've tested things, we have successfully tested the stochastic model. That was one of our big benchmarks. And we've also tested dipping faults. The thing where we didn't quite come to a conclusion is the material contrast case. So we might want to possibly leave that for later, although of course it has an important effect, or can have an important effect on earthquake triggering. So just wanted to bring up that 2 out of those 3. And in terms of parallelizing the code, Michael, a super efficient has said that it would take him 6 months, but we've never had 6 months of money. So if someone wanted to suddenly cure with 6 months of money, that would be great.
Okay, but Ruth, you just said the material contrast across the fault has not gone through one of your validation or verification efforts. Is that right?
Well, we did do it, but I'm not sure that we resolved the rupture well. So that was one of our ones in our list of the many benchmarks that we've done where we don't advertise that people should do it. We probably need to figure out a better way to look at the resolution. And Ralph and Steve and Kim, of course, are all very involved in this group, and Brad also. So we should probably sit down, have our group sit down and look at that again and see if there's a way that we can ensure that we're all producing results that are super reliable. But the other methods, the stochastic stuff that Kim brought up, and then the dipping faults we have successfully done.
So, Kim, have you tried the rough fault version with a Splay or something else coming off of that yet?
Here.
You should talk to Steve about. He's the guy to talk to about the rough fault modeling. So, but I don't believe that they have actually looked at Splays. But Steve can say more about that.
No. So Steve's shaking his head no. All right. From the other modelers or people that do that work in the audience here.
There is
What?
somebody else
Oh.
on the phone?
No, this is just Bruce again. So the person that could have possibly done it would be Shou Ma, because he, in his finite element code, he does complicated geometry, so he might have possibly done it, but Steve and Kim would know the answer to that.
I've never seen him present that, and I go to pretty much every conference talk of his. So.
Okay, but for the others, modeler types in the audience, what is you think the best use of the dynamic rupture models now for what we're trying to get at? So you've seen our problems, you know what the focus is. Is there areas where you would say this is the best use of this or where it will be most informative for us? You know,
This is Brad Agard. I think one of the best ways that the dynamic rupture models can help inform the process is when you have all of these sort of splay faults, complex ruptures, and you have constraints on the regional stress field, you can look and get a good handle on, you know, what ruptures are likely to happen. And if you look at the dynamics, and you can never get a rupture to propagate from one onto a branch because of the regional stress field, you see it's sort of being de-stressed rather than the stress increasing. That's going to give you a lot of confidence that that scenario is going to have a very low probability compared to other scenarios where the stresses are increasing. There's still a lot of sort of wiggle room in terms of what the stochastic stress field is, where you start the rupture, how fast is the rupture going, what's the stress drop. That's a very big parameter space, but understanding sort of the dynamics of stress increases, the dynamic stresses increases and decreases on these various splays, and whether they're likely to go or unlikely to go, that's going to be a much more robust conclusion that can directly help inform the probabilities of these various scenarios.
So basically put the regional stress field issue quite high on the list.
but that's source characterization fundamentally, and I think they want, those guys are after that. So I think that's important if that's one of the key values or information that's going to come out. But now on ground motion, what can we get out of this? Steve, did you want to add something to that?
This is Steve Thompson. In looking through the various velocity models that have been proposed for Diablo Canyon, in the upper kilometer, 1.5 kilometers across the Hosgri, there's the margin of the Santa Maria Basin, which is a stark velocity contrast. But below, through the remainder of the seismogenic crust, all of this PG, Edge, Rice University studies, they had pretty homogeneous velocities across this whole fault system. So to the extent that these experiments are trying to inform us about Diablo Canyon specifically, consider that no one's really hypothesizing big velocity contrasts across that fault, at least fault zone, at least at seismogenic depths.
Let's see if there's any. Kim, yeah.
Julian didn't mention another project that we have going on. Oh, you talked about the San Jacinto Fault.
Yes.
One thing that we hope that I'm partly involved in is we hope to compare the ground motions to precariously balanced rocks. Once we get some robust estimates of the ground motions, either purely dynamically or combined with these funny scattering functions from the SDSU module for the higher frequencies. So hopefully we'll get some results on that over the next months as well, and after that some comparisons to quite a few precariously balanced rocks in the surroundings of the San Jacinto Fault.
Yeah, so that definitely is all the higher resolution models are running. And so yeah, this is something. There's big old distribution of precariously balanced rocks on, not so much in the red area as it turns out, but using I guess I saw fragile geologic features later on the agenda for this talk, and I assumed that it meant such things as precariously balanced rocks. So it's definitely part of the plan for this to make that comparison, and so even if I can't go to super high frequencies with the dynamic models, using those precarious rocks as sort of crude ground motion, indicators, and comparing them to the models is another plausibility check that I guess could be made with even lower frequency models and other sites that might have this splay geometry. I don't know if there are precarious rocks near any of your target areas. I assume there are, since they're on the agenda.
You'll hear about that next. But
Cool.
we got to move on, so we're out of time. Thank you, Julian.
All right.